So today we're going to be looking at this kind of idea of impulse, essentially forces applied over a certain amount of time, or think of it differently. What kind of force do we is exerted when momentum changes in a certain amount of time? Uh, so really, the equation we're kind of using here, I is one of the few physics initials, abbreviations that actually match what it is. So capital I, that's impulse. It is a vector, so we kind of draw that kind of half arrow above it. It's equal to force times the change in time, or the time interval that the force is applied for. It's kind of like work in that we had force times distance there. Here it's force times time. Really what we're going to see when we take that force times the change of time is we should be able to find the change in momentum for the object. So we're back looking at one object only. So we're not really, we're talking about collisions that they cause a change of momentum, um, but we're really just focusing on one thing here. So down at the bottom there, there's a question. You push on a 22 kilogram shopping cart with a force of 6.5 newtons. If you push for 1.9 seconds, I know I typically put distance down here, but pushing for 1.9 seconds works as well. What's the magnitude of the impulse, or how much impulse was there? So really, in this case, they give us a force. They give us a time interval. Pretend that's a delta t. Mass in this case we really don't need, because to find impulse I just need force times change in time. So impulse is equal to force times change in time, so 6.5 newtons times a time interval of 1.9 seconds. Bring my calculator over here. 6.5 times 1.9. Look like 12.35 is what I'm looking at. So now for a unit, if impulse is the same as essentially momentum, we're working with kilogram meters per second. All right. So that's the impulse. This is essentially how much force this thing is experiencing, in a unit of time. Really, if I wanted to do the kind of look at unit analysis here. So momentum, we said, were kilograms meters per second. Newtons are kilogram meters per second squared. Time is in seconds. So kind of proving that newtons, that force times time equals momentum, just looking at the units here. So if I, break a newton down into kilogram meters per second, I'm taking that times time, which is in, seconds squared. If I take that times time, which is in seconds, seconds on top, seconds squared on the bottom, that's going to cancel out the square. Kilogram meters per second, kilogram meters per second. Impulse, momentum, pretty much the same thing. All right, so that's kind of using that equation there. And there's another way that we can kind of look at that equation. I find there we go. Make this a little bit better. There we go. All right, so new question. Let me get I equals F change in T equals change in B. All right. Force acts on a bicycle for 12 seconds. All right. There's my bicycle. And we said that was for 12 seconds. So that's my change in time. And changes its momentum from, essentially we started off with, so momentum initial from 15 kilogram meters per second. We ended with a momentum of 38 kilogram meters per second. They want to know how much force acted on the bicycle there. All right, so look at this. I don't need to find impulse at all. So really what I'm going to be looking at is force times change in time equals change in momentum. In this case, I'm looking for the force. So to get force by itself, I'm going to divide both sides by change in time. That cancels there. So force is equal to change in momentum over change in time. All right, so in this case, keep in mind that change in is the final value for whatever we're talking about minus the initial or starting. All right, so I'm looking for force here. So change in momentum, it's the final minus the initial. So it's 38 kilogram meters per second minus the starting, which was 15 kilogram meters per second, close parentheses, divided by the time, which we said was 12 seconds. So in this case, all right, 38 minus 12, I'm going to guess is 23 kilogram meters per second over 12 seconds. 23 divided by 12, I'm going to guess is pretty close to 2, about 1.9. 12. Yeah, 1.92, we'll call that. All right, so now my unit here is kilogram meters per second, or I know that newtons are the same as kilogram meters per second squared, which is really what I'm getting there. So 1.92 newtons. That's a force. So really, this thing is kind of useful for finding force or finding total impulse, finding change in momentum. I can kind of go back and forth between some of these things. Pretty easy. So that's impulse. That's kind of the last part of momentum. We really need to talk about, we talked about elastic and inelastic collisions. Really, impulse is useful because if I increase, so kind of going back to this part here, that the force is equal to the change in velocity, sorry, the change in momentum over change in time. This part right here, the fact that we're dividing by time is why two things are really important, namely seat belts and airbags. Both of these allow the same change of momentum to take place, but these things really increase that change in time. So we can't really change the change of momentum, when there's a car accident. But what we can do is we can change the amount of time that that momentum is changed over. So by making this number bigger, we're going to make the force smaller because we're dividing by a bigger number. And less force means there's less incidence of injury. So just kind of give you like a real world example of where like this whole idea of impulse matters. That's it. Trampolines also work because of impulse. You're having the same change of momentum, but the amount of time it takes to stretch a trampoline from, we'll go with there, that's more horizontal, to, something more like that. It takes time to stretch that far. Anyway, I'm done babbling. Good luck with the practice.